Okay, so hello everybody and welcome to the new quarter, insofar as that has much meaning these days. So today we're very happy to have Jose Bernal from Johns Hopkins, who will talk to us about the trouble with H0. So go for it.
Okay. Well, thank you everyone for having me here. Even though it's through Zoom, it's a pleasure for me to talk about the work that I've been doing related with the Hubble constant tension with some of my collaborators. And well, I'm sure that by now you've heard many times that we are already on the regime of precision cosmology, in which thanks to a tremendous effort by observationalists and also theorists, we have been able to exploit to extreme precision the information encoded in the cosmic background, the clustering of matter and the baryon acoustic oscillations, gravitational lensing, supernova 1A, and even lately gravitational waves. And thanks to all this effort by improving the experiments, but also improving the modeling of the observations, we have established a standard cosmological model, which is the lambda quantum matter. And this model provides an excellent reproduction of most of the observation, but has still two big problems. One of them is more in the theoretical side, and the problem, this is intrinsic to lambda CDM, and this is because this is a phenomenological model and does not pretend to explain the nature of dark matter or dark energy, or even the conditions and the microscopic physics at the primordial universe. But the one that I'm going to focus more today is the one that is more in the observational side, because there are some persistent discrepancies between different experiments and cosmological probes, which, as I will tell just now, we can frame as a tension between experiments that depend on physics of the high-redshift universe and physics of the low-redshift universe. The most relevant tension in this sense is the one that I'm going to talk more about today, which is the Hubble constant tension. But there's also the problem with weak lensing experiments, which is related with this parameter combination of sigma 8 and omega matter, which basically encodes the information of the amplitude of the perturbations, the density perturbations today. And in my opinion, what we can do as cosmologists in order to help with these problems of lambda CDM and try to reconcile these measurements is, first of all, improving the observations of the cosmological observables that we are already exploiting. This would be with better modeling or with better experiments. But we can also explore and look for new cosmological probes and sources of information that will help us by providing independent measurements and also accessing to information in different regimes. And also, of course, exploring new models beyond lambda CDM that will help to find the answer for those incognitas, and also to find a way to reconcile these measurements. But let me move on to the current landscape, the experimental measurements of the Hubble constant. Here I have adapted a very nice plot from a recent review by Eleonora y Valentino et al. And I'm basically showing 1 sigma confidence level measurements on the Hubble constant by very different experiments. Here are the ones that are related with physics of the early universe, this one related with the distance ladder, strong lensing time delays, and the late universe. And as you can see, basically from this line to the right, they are related to the low redshift universe. And you can see that they are all clusters around this blue band, which corresponds to the consensus measurement by SUS. And on the other hand, the measurements that depend on the early universe are clustered around this red shade. That is the one by Planck when lambda CDM is assumed. So there's a lot of information in this plot, but basically, besides this confirmation that it seems to be the tension between experiments probing the physics in the low redshift universe, preferring high values of the Hubble constant, and experiments probing the low redshift universe, the high redshift universe, which yield results of the Hubble constant tension that are low values. This is also a hint that this tension is strongly model dependent, because first of all these measurements that are depending on the local distance ladder do not depend on cosmology. The ones on the strong lensing time delays slightly depend on cosmology, because you need to assume expansion history up to the position of the sources and the lenses. But the ones that depend on the early universe strongly depend on cosmology, because basically you are evolving the whole universe and measuring, for example, in the case of the CMB, around redshift 1000, and you need to still reconstruct the whole universe in order to infer low redshift quantities, such as is the case of the Hubble constant. But also from this measurement, we can see that these are the measurements with different data sets and analysis choices from Planck. And this is from other CMB experiments. And as you can see, the problem is not related with only Planck anymore. And not even with the CMB, because analyzing the galaxy distribution with priors from Big Bang nucleosynthesis, and some of these analyses have been done by people here in Stanford, you can see that in this case, all the measurements are consistent between them with not a big scatter. So it doesn't seem that it's related with systematics of different observables related with the high redshift universe, but also not related with the low redshift universe, because this is a whole plethora of measurements related with the source data, with different analysis choices, different calibrators, different reanalysis by different and independent groups. And the scatter is very small, and all of them are consistent between them. Moreover, if not CFITs, but the tip of the red giant branch is used to calibrate the supernovae, it's true that the results are a bit lower and that there are a bigger scatter. And this is because it depends on the reddening towards the large Magellanic Cloud, which is the data that is used in order to calibrate the tip of the red giant branch and supernovae. In this case, it's not clear what is the correct modeling for that reddening. And as far as I know, the jury is still out for this case. They are still waiting for a definitive determination of that reddening. There are other measurements that are very promising, but are still not consistent. They seem to be clustered around high values, but the error bars are still too high. And I also wanted to mention the case and the recent developments in the measurement with from strong lensing time delays that have been performed mostly by the TD Cosmi and Holy Cow collaborations. And in this case, they were very competitive results clustered around high values of each node, but the recent analysis in which they also consider the internal massive degeneracy of the lenses, in this case, the error bars were much larger due to this marginalizing over that potential source of confusion. And there are two main measurements in this case. One, which is the dashed line, which depends only on measurements by TV Cosmo, and the other one, which is the solid yellow line, is adding the anisotropic velocity dispersion and the mass profiles from the SLAX galaxy sample, which is a lower redshift galaxy sample, and assuming that these galaxies and the lenses used in TD Cosmo come from the same sample in the end. And as you can see, the error bars are a bit smaller, but the main change is that the central value is shifted toward low redshift. So I guess that we will need to wait a bit longer to see what is the final value preferred by strong lensing time delays. Okay, but I've said already that this tension is model dependent. So let me summarize very quickly how we can infer the Hubble constant from the CMB and what is the freedom that we have to play with the CMB in order to reconcile these measurements. The Hubble constant is the place that most directly affects the CMB power spectrum is in the position of the first acoustic peak. And we measure the angular scale of that first acoustic peak very well. That scale is measured with 0.04% precision. And it's basically the ratio between the sun horizon at decoupling and the co-moving angular diameter distance to decoupling. So basically this is one which depends from the beginning of the universe until decoupling, and the other one is from today to decoupling. And basically here, one of them is the integral of the sun speed over the expansion rate, and the other one is the integral of the speed of light over the expansion rate. The problem is that if we want to have a high Hubble constant, that will affect primarily the distance that we measure to decoupling if we don't change anything else. So then we need to either change the pre-recombination physics in order to reduce the sun horizon at the decoupling and maintain this ratio with the same value, or what we can do is play with expansion rate after recombination so that the final distance to decoupling is the same. That latter choice, that option that I mentioned, could be basically changing the expansion rate post-recombination. But before recombination, since there are more dynamics involved on the sun horizon, we can play a bit more. We can change the redshift of the decoupling. We can change the sound speed of the baryon photon plasma. But in this case, these two quantities are very constrained with the current knowledge that we have about the physics before recombination, and more especially because we have very good measurements of the CMB. So changing these two is very, very difficult. So it seems that the only option that we have in the end is changing the expansion rate, boosting it in such a way that this integral yields lower values for the sun horizon at decoupling. The trick here is doing this without messing the rest of the cosmic microwave background isotropies, because changing the expansion rate will also affect, for example, the diffusion scale and the potential envelope, which depends on the redshift of equality and the horizon scale at equality. So this is the trick, and this is where most of the theoretical efforts are invested right now. And if you want to read a very good summary about the potential possibilities that would keep this ratio equal and that are don't mess the rest of the power spectrum, I recommend you to read this nice paper, the Hubble Hunter's Guide by Knox and Milea. But let me focus on what we can do at the low redshift and how can we measure the expansion rate at low redshift. In order to do that, we basically can use the standard rulers and the standard candles, and the main ones that we have right now are the BAO and supernovae type 1a respectively. And the best thing about these two is that they are very complementary. In the case of the BAO, we can constrain the amplitude of the expansion rate. The problem is that since the sampling in redshift is not abundant enough, we are not very sensitive to measure the shape of this expansion rate once we give a bit of freedom. For example, for lambda CDM, we can constrain omega matter very well. But for extended models, this is a bit more challenging. On the contrary, we don't know what is the absolute magnitude of the supernovae, so we can't constrain the amplitude of the expansion rate. But since the sampling in redshift that we have from this data is very, very abundant, we can constrain very efficiently the shape of the expansion history. And now let me try to explain why the BAO are, in my opinion, with the CMB, the most key measurement that we have right now in order to determine the possible solutions for the Hubble constant tension. And this is because basically BAO connect very efficiently the high redshift universe and the low redshift universe. But first of all, let me go and explain how we exploit the baryon acoustic oscillations at low redshift with galaxy surveys. Basically, what we are trying to target is the fact that the acoustic oscillations are frozen in the matter over densities after recombination, and this basically provides us a standard ruler because there's a slight increase in the chance to find a galaxy at a distance which corresponds to the sun horizon at radiation drag, which is very similar to the sun horizon at decoupling. It's just a bit later. The problem is that we can observe this as the overdensities grow with galaxy surveys, but these observations are taken in redshift space. And the predictions that we can do with efficiency are in physical scales. There is the power spectrum or the correlation functions that we can compute with our Boltzmann codes. Therefore, in order to analyze this data, what we need to do is transform these redshifts into distances so that we can create a three-dimensional map with physical distances. The problem is that here, to do this transformation, we need to assume a fiducial cosmology. And of course, this cosmology is most likely to be incorrect, even if just by a small difference with respect to the actual cosmology that the universe have. And this will introduce artificial distortions in our map in the next way. So in order to explain how this distorts the map that we reconstruct from the observations, let me first assume that we only have a spherical overdensity of galaxies, and we are looking at this from below. So this would be the direction transverse to the line of sight, and this would be the direction along the line of sight. And in blue, I'm going to reproduce here and to illustrate the real overdensities. Now, we have the observations in terms of angular separations and redshift, as I was saying before, and in order to transform that into distances, we use, for the transverse distances, the co-moving angular diameter distance and the angular separation, and for the parallel distances along the line of sight, we use the redshift separation and the expansion rate. So when we do this, if we have assumed a wrong cosmology, this is known as the Alcock-Paczynski effect. Basically, we introduce an anisotropy in this overdensity because the difference in the predictions for these quantities for different cosmologies are different. They affect different to the distances and to the Hubble rate. But moreover, since we are assuming a fiducial cosmology, what we interpret as the sun horizon at radiation drag also change with respect to the real map. So in this case, we have an isotropic dilation of this overdensity, or at least of how we understand it. Now, this seems like a problem in order to exploit the observation from galaxy surveys that we have, but it's actually a good thing because basically what we are going to target with BAO measurements is this misestimation of the real cosmology that we have in the universe. Basically, we target this error in the Alcock-Paczynski effect and in the data distortion in our reconstruction of the maps. And we can do that because we can model these distortions in our scales very efficiently with linear parameters, which I call, and they are mainly called rescaling parameters. And these are these alpha perpendicular and alpha parallel, that basically they are linear corrections for these quantities that I showed you before. Therefore, this is why alpha perpendicular is the ratio between the moving angular diameter distance to the redshift of the galaxy sample over the sun horizon at radiation drag over the fiducial ratio of these two. And for the parallel is the same, but since it depends on the Hubble rate, is the Hubble rate in terms of the distance. Now, why do we have also here the sun horizon? And it's because individually for these two, we can distinguish the effect of the Alcock-Paczynski effect and the effect from the isotropic dilation. That's why we need to have both at the same time. But this is good because we can target at the same time low redshift physics, which could be basically these distances and the Hubble rate, and high redshift physics, because this depends on the physics, the value of this sun horizon depends on the physics before recombination. And okay, now that we have modeled this distortion, the way BAO are measured basically is computing a template for the power spectrum in this fiducial cosmology, and basically rescaling that template with this parameter and marginalizing over the broadband in such a way that basically what we are left with is only the BAO oscillations in the power spectrum, and what we do is distort that in an anisotropic way so that we fit the measured power spectrum. And in this way, BAO attempt to provide a model-independent measurement with information of the expansion history of the universe, with a normalization in terms of the product of the sun horizon at radiation drag and the Hubble constant. Now, remember about this product because it's going to appear many, many times in the rest of the talk. But I don't know if you notice, but here it seems that I have said two contradictory things. First, I said that the measurement of the BAO comes from a template measured in a specific assumed fiducial cosmology that most of the times is lambda CDM with the best fit parameters of Planck or very close to it. And then BAO attempt to provide model-independent measurements, and in the end, they are actually used as model-independent. We use this alpha parameter in our Monte Carlo Markov chains for any model that we are fitting to the observations. But this is not necessarily true. We don't know how dependent the alpha measurements are on on the choice of the fiducial cosmology. And in order to answer that, basically what I did was check this empirically. So what I did was for different cosmological models attempting to solve the Hubble constant tension, I generated synthetic power spectra and analyzed them and feed the BAO alpha parameters, assuming always the same template, the one that is used right now, which is for lambda CDM Planck's best fit. And here, basically, the results of that analysis that I did. Let me walk you through this plot because there are many things. So first of all, I'm plotting the 1 and 2 sigma marginalized constraints on alpha parallel and alpha perpendicular, and each column corresponds to a different experiment. Each row corresponds to a different cosmological model. This could be lambda CDM. This could be with a different number of relativistic species. This would correspond to early dark energy models. And this would correspond to a model that introduces an interaction between the dark energy and the dark matter and neutrinos in order to change the correspondence between the physical size of the sun horizon and the angular scale that we measure. And in each of the panels, I have results for a good fit to Planck in blue, and a bad fit, a really bad fit for to Planck in red. And for each cases, you don't need to compare the red and blue contours. What you need to compare is our maximum posterior values, which are these dots, with the true values that we know because we have generated this data synthetically, knowing the actual cosmological parameters for each case, which are the stars. And as you can see, in all cases, even for the very bad fits to Planck, which are, of course, very disfavored cases, we find very good agreement, except for this case, these two cases, which I think I remember these are like more than 70 sigma away from Planck. And the bias that we have in our BAO measurements is of 1 sigma. So in the end, this is basically a very strong indication that the BAO measurements are robust and are unbiased and can be used in a model-independent way, even for cosmology that are very, very different than the fiducial cosmology that was chosen to do the BAO analysis. The only problem that you may have is that in the very far tails of your distribution for your cosmological parameters, but that's not going to bias in the end your results for the cosmological model that you may want to fit with Monte Carlo Markov chains.
In these different cosmologies that you're exploring here,
yeah,
are they all just lambda CDM with different cosmological parameters, or are they qualitatively very different? You know, like an early dark energy model, or one of these weird, you know, I don't know. Like there are a bunch of different weird cosmologies that people have proposed for the Hubble tension, right? So
yeah. So this row is lambda CDM with different cosmological parameters. This would be lambda CDM, and for the blue one, n effective is around 3, so it's very close to lambda CDM. But the red one is 3.5, so it's already very disfavored. And this is an early dark energy model, the one developed by Tanvi Carval, Vivian Poulan, Tristan Smith, Mark Minkowski, and company. And this would be with this interaction between neutrinos and dark matter. This is what I would call the weirder model because it's the one that introduces more differences with respect to lambda CDM.
Okay, thank you.
But in all cases, especially in this one, and I have a plot about this in the paper, the BAO feature in the power spectrum changes a lot. So we are checking what we wanted to check with this exercise. Okay, so let me go back to how can we, with these measurements, constrain the expansion rate at low redshift. And now we know that the BAO normalization is in terms of this product of the sun horizon at radiation drag and the Hubble constant, and that BAO are actually model independent. So with this, now having BAO and supernovae, we can build the cosmic distance ladder in a direct way. So that would be starting from today towards higher redshift, calibrating the supernovae with the Hubble constant, and then with that, will you calibrate the BAO. But we can play the same game in the opposite direction. We can go from the early universe and take a prior on the sun horizon at radiation drag, or a prior from VBAC nucleosynthesis, and with that calibrate the BAO, and with that correspondingly we will calibrate supernovae and the Hubble constant. And this is called the inverse distance ladder. And in the end, of course, this is in the same quantity, so these two quantities need to coincide, and we can reframe the problem of the matching the Hubble constant from different experiments and as matching these two anchors of the cosmic distance ladder, which when we left both of them free, we can constrain them, this product with BAO, in what we called in this paper in 2017 the low redshift standard order. Now, this is basically what I did in 2016, and assuming a very generic and free expansion rate parameterization, I did cubic splines. Basically, I chose some fixed nodes, and that the expansion rate at those specific redshifts was the free parameter, and then I will interpolate between them with cubic splines. I feed that parameterization to BAO and supernovae, marginalizing over the sun horizon at radiation drag and the Hubble parameter, the Hubble constant. And here I'm showing those results in pink and comparing them with a sun horizon at radiation drag from Planck 2015, analyzed marginalizing over any physics after recombination, and also with the measurements from SUS at that time. And as you can see, basically, depending on with which data I combine this BAO and supernovae data, I have two very different and intention results for the H node and the sun horizon at radiation drag. So basically, this was the first indication that the Hubble constant was a mismatch between the two anchors of the distance ladder. Moreover, and that we need to reduce the value of the sun horizon at radiation drag in order to match H naught, a higher H naught than predicted by lambda CDM with Planck. Moreover, here I'm plotting the resulting splines and the constraints in the shape of the expansion rate with respect to Planck. The best fit from my analysis is in black, and each small and thin red line are different splines from the 1 sigma preferred region of our analysis. And basically we saw that in this case, up to redshift around 0.6, the shape of the expansion history is very constrained to be like lambda CDM, and that the product of the sun horizon at radiation drag and the Hubble constant is constrained below the 2% precision. And this was a strong indication that there wasn't a lot of freedom in the expansion history to be modified with, I don't know, dynamical dark energy or things like that to alleviate this tension. But what was a hint in 2016 now is, at least for me, much more certain, because after 5 years, we have much more data and better data. And also we have improved the parameterization of the expansion rate. And this is basically what I'm showing here. Here I'm again showing the constraints on the shape of the expansion history. And in red is the prediction by Planck. In blue are the results from BAO and supernovae, assuming lambda CDM. And in this case, already you can see that the results are very compatible, and especially the error bars for the product of the two anchors of the distance ladder is very similar. But what was surprising to me is that in this case, that the parameterization of the expansion rate is even more general than it was in my work in 2016, because in this case, instead of using splines, I'm using flex nodes, which is almost the same, but in this case, the nodes of those splines also vary their position in redshift, so it's even more general. And moreover, we drop the assumption that the universe was flat. In this case, you can see that the constraints on deviations from the shape, on deviations of the shape of the expansion history with respect to lambda CDM are even stronger than they were before. And now we are reaching a redshift of 2.4 and not stopped at like around 0.6. So these results are much more powerful. I did this analysis with a code that will be public when this paper is accepted. That is Mabel, and if you want to use it before, just drop me an email. We can talk about that. But what was surprising to me is that the constraints on the product of the sun horizon and age are almost the same than assuming lambda CDM, and that our constraints on the curvature, given how free our model was, were also very powerful. This was like having something compatible with flatness with 0.1, with having this much freedom was very, very surprising to me. So basically for me, this is the final indication that BAO and supernovae strongly disfavor any low redshift deviation and therefore solution for the Hubble constant tension, and that the changes in the early universe are required in order to solve this tension. Now, this is true, but there are some exceptions that, at least in my opinion, are unlikely to be valid or in the end to be the final solution, but that one needs to take into consideration before rule them out. The first of them would be basically having a boost on the expansion history in the very local universe, such as it wouldn't affect the distances, and basically it would be having a high value for the local universe of each node, and then for any cosmological quantity that will drop dramatically and behave like if the Hubble constant could be 67. But this is of course super fine-tuned because having this boost right now is very, very unlikely. The other one would be modified gravity affecting the physics or the stellar physics in CFITs and the tip of the red giant branch. Therefore, this would affect the calibration, and having different mechanisms for the screening of these modified gravity theories. Basically, it could have explained, and the value of each node from SUS and the Carnegie Chicago Hubble program basically can be lowered. But the only problem is that in this case, you will need to screen and explain with modified gravity different physics and at very different regimes. So it's, again, it doesn't work as well as one would think at the beginning, and it doesn't reconcile them with the values predicted by the CNV. Another exception would be that somehow any physical model would affect the standard ruler for BAO and change it from the sun horizon at radiation drag and at decoupling, and what we have right now. But I've never heard about any viable physical model that does this, at least with the huge difference that we have, because we need around like a 7% change in the sun horizon. Or also, the other possibility is that there's a violation of the distance duality relation, because basically all our analysis is combining BAO and supernovae. This is combining angular diameter distance and luminosity distances. And if there's a violation of the distance duality relation, basically our combination and our analysis would be invalid. But this wouldn't ensure that the Hubble constant would be solved. That it just would show that we will need to redo our analysis.
So now, just to ask on that point, by a violation of the distance duality relation, do you mean that somehow GR breaks down or something, or what would actually cause that?
I don't know. I think that there are some weird gravitational like GR modification from GR that would explain this.
Okay, so it is modifying GR.
But I don't know about any specific model.
Thanks.
And to be fair, all agnostic and phenomenological tests of the validity of the distance duality relation have been passed. So I don't expect this relation to be violated, at least as much as it should be in order to invalidate this analysis.
Right, thanks.
Okay. So before we were talking about, in 2016, we had this certainty up to redshift 0.6. Now we have it up to redshift 2.4. Can we go beyond? With galaxy surveys, it could be a bit difficult because as redshift increases, the galaxies become fainter and sparser for cosmological analysis, but with line intensity mapping, maybe it will be. And this is what I explored in 2019 in a couple projects. And this is a similar analysis with forecasts from BAO analysis with line intensity mapping with lines related with star formation. These are for some futuristic experiments, so don't expect this precision up to resin 9 just now, but I'm very excited about all the capabilities that line intensity mapping will have. And in the end, in the future, probably they will be allow us to reach with model independent analysis to constrain the expansion history up to redshift around 9, and in the end, bridge between the early and the late universe and probe post-recombination solutions of the Hubble constant tension. Okay, but so far, I've been talking all the time in terms of distances, related only the Hubble constant tension to distances. And the thing is that the Hubble constant also affects other quantities, such as time. So I think, and this has been most of the times overlooked because we don't have very good ways to measure times in the universe. We can measure very well redshifts, and then assuming a model, we can relate that with times, basically with this expression that depends on the shape of the expansion history and the Hubble constant. And the age of the universe would basically...
Sorry, just to ask at this point, what does the E notation mean?
Sorry?
What is the EZ notation?
Basically, this is, I have it here, is the here, sorry. Is the ratio between the...
Fine. Thanks.
No problem. Okay, so basically the age of the universe would be doing this interval up to infinite redshift, but in the end this is going to be completely dominated by redshift below few tenths because the integrand goes to 0. And here I plot you and I show the values of the age of the universe as we vary the Hubble constant, omega matter, and the equation of state of dark energy, constant in this case. And as you can see, in most of the cases, it's mostly sensitive to H0. It's also somehow sensitive to omega matter, but the largest sensitivity is to H0. And as you could be probably already be anticipating, if we have this strong difference between the two determinations of H0 that we have, this corresponds to a very different predictions for the age of the universe, basically separated by 1 billion years. And what is funny about this is that no matter how you change the early universe or pre-recombination physics that were the changes to lambda CDM that I mentioned before that needed to be changed in order to solve the Hubble constant tension, those changes are not going to directly affect the age of the universe. And the change here would basically be only through the changes in H0. Okay, but how can we infer in an independent way and as much model independent from cosmology that we can? As I said before, you can take your model and do that integral from some for some cosmological parameters. But I also would like to be as independent as possible of the cosmological probes that we already use a lot for determining and taking these measurements of the Hubble constant. And we can do that basically from the inferred age of the oldest globular clusters. Basically, if we can infer the age of these oldest globular clusters, that will give us already a lower limit for the age of the universe, because of course these stars can't be formed before the universe. And but we can even go further because we can estimate the time gap between the formation of the universe and the formation of these globular clusters. And we can do that basically estimating a redshift for formation for these globular clusters, which we assume to be between redshift 11 and 30. And the lower limit is because there are indications and observations of galaxies that are very likely to have already globular clusters at redshift 11, and at redshift 30 because it's very hard for stars to form before this redshift, and even if they do, they would be population 3 stars and not the stars that in the end would be in the globular clusters and survive in the globular clusters that we can observe and study today. And we marginalize basically over this, taking the question, the integral that I showed you before, we marginalize again over this formation time and over the cosmological parameters of relevance over very broad ranges. And basically, this is the distribution that we find for the time gap between the formation of the universe and the formation of these globular clusters. But now is the problem, like we just pushed the problem of inferring the age of the universe to inferring the age of these globular clusters. And basically, we did that exploiting all the information in the color magnitude diagram of the globular clusters and analyzing them in a Bayesian way with isochrons. And here you can see how the color magnitude diagram, this is for theoretical isochrons, but these isochrons model very well the color magnitude diagrams of these globular clusters. And here you can see how especially the turn-off of the main sequence is very, very sensitive to the age. And what we did that is not so common in this kind of analysis also was include the red giant branch, because even though it is not very sensitive to age, it will be very sensitive to the metallicity and will help to solve the degeneracy between the age of the metallicity and the metallicity. So basically, we did this analysis and select the oldest globular clusters basically by choosing the ones with lowest metallicities. And after marginalizing over metallicity, the distance to the globular clusters, the abundance of the alpha elements, and the absorption and reddening to the globular clusters, we found the age of these oldest globular clusters. And after convoluting this distribution with the time gap that I showed you before, we found that the age of the universe is, at least from our information from globular clusters, 13.5 billion years, plus minus 0.15, and this could be the statistical error, plus minus 0.23 or 33. This is the systematic error, and the results depend on whether you use external data or not. But we are very happy about this because even though right now this is dominated still by systematic, we already reduced in this work led by David Balsin this year, the main source of systematics that was the envelope, the convention envelope, and the mixing length theory of the stars. And right now we are mostly left, and this is by far right now the dominant systematic, with uncertainties in the nuclear rates and opacities of the stars. And we are working right now in reducing those systematics. But we can study already what information we can get and what implications have this measurement for cosmology. And here, basically, I'm plotting similar to what I did before, but instead of comparing the Hubble constant tension with the sun horizon, I'm doing it now with the age of the universe. And in this case, I'm showing the results with the statistical errors in dashed lines, and the whole set regions is accounting also for the systematic errors. And here I'm showing only 1 sigma errors. So basically, the conclusion that we have is that these are more problems in order for a cosmological model to be able to solve the Hubble constant tension, because as I said before, we need to change pre-recombination physics, but these don't change TU. And if we are going to obtain basically a Hubble constant that is around 74, and this needs to be consistent at low redshift with BAO and supernovae, but this analysis is also valid for any changes before recombination. So for example, for an early dark energy model, this measurement could still be completely valid for that. So we have seen that in that case, we will need to have been measured or have obtained an age of the universe much, much lower than we did. So basically, though the error bars right now are a bit too large, here I have the measurement for the product of the H0 and the age of the universe and the age of the universe alone. If you compare SUS with the prediction from lambda CDM or an early dark energy from Planck and our results from globular clusters, this is in tension. So basically, this still is preliminary because the errors are too large, but this is already a possible hint for the need of not only pre-recombination modifications to lambda CDM, but also post-recombination physics in order to solve the Hubble constant tension. And now they are like a completely different kind of measurement that has a very important role on this problem and to determine which models will be valid or not. Okay, so this is one of the main conclusions that I want to tell you this time. But let me go to what I think, and we also explore this in this paper. And I think that is a very cool and effective way to plot and visualize constraints, specifically in this case for the Hubble constant tension, but that can be extended for any over-constrained system. So as you may have noticed, I've been talking all the time about over-constrained triads. We have a measurement of the sun horizon from the early universe, of age from the local measurement, and on the product of the two from BAO supernovae. We have the same in the case for the age of the universe. We have the measurement of the Hubble constant. With globular clusters, we can infer the age of the universe, and the product of the two, we can infer it, assuming a cosmological model from BAO and supernovae. And I haven't talked about that, but we can do the similar thing with omega matter and h squared. And this case with over-constrained triads was already, this has already happened in cosmology. And in the 1999, Bernal et al. In a science paper, they proposed to plot the results regarding the density parameter, the density parameters, omega matter, omega lambda, and omega curvature, that has to be sum 1 due to the sum rule in a ternary plot. Basically, these ternary plots are a plane between the three axes in a three-dimensional, and that all the points in that plane add to 1. So here, this line, for example, is the one that corresponds to constant omega k, but omega matter and omega lambda will change in such a way that all points will correspond to 1 in the end. And already in 1999, this was a very effective way to show that existing measurements at that time already preferred lambda CDM as the preferred quantity. Now, we have the triads in this case with products instead of with sums, so we need to take logarithms, but we can do the same and transform this two-dimensional plot, in which this case, this is the constraint on the product, to a ternary plot, taking the logarithms. And in this case, all points in this triangle sum to 0. And this is what I like to call the new cosmic triangles as as reference for that paper from Bernal et al. In 1999. And in this case, I think that the visualization of the consistency and the tension is clearer because I show here the constant values of H naught, but you can see here, for example, that the early dark energy contour elongates in the direction of constant omega matter, which corresponds to constant H naught T nu. And you have here the value of the age of the universe that should be shifted here in order to coincide with that. And this is the case for the age of the universe. But as I said, we can play the same game with the three triads that we have, and we have these three cosmological triangles. And comparing these three at the same time is very illuminating to me, because we can see how the main battlefield of the Hubble constant that we have had during the last years, which is in terms of the matching the two anchors of the distance ladder, as I said before. Here we can see very well the tension that are between Planck, assuming lambda CDM, SUS, and BAO and supernovae. The hole between the three measurements is very, very large. And in this case, early dark energy is very effective in order to solve this tension and to close this hole, because you can see how the sun horizon at radiation drag changes so much that in the end, even though not perfectly consistent, but is very efficient to close this gap. In the case of the omega matter, the change is slower, but also the initial tension between the three measurements were smaller, so it's still convincing. The problem, and where I think that early dark energy is not enough in order to reconcile our measurements, is when we take into account also the age of the universe. And as you see here, in the plane with the age of the universe and the product with Hubble constant, is still like early dark energy is not powerful at all in order to reconcile the measurements, and still we are very far to reconcile with SUS, Planck, BAO and supernovae, and the new measurement with globular clusters. And therefore, this is why I think that with having these new cosmic triangles, we can visualize tensions and see how we need to change, or which new physics we need to introduce in our models in order to modify these values and finally reconcile all measurements. Okay, so I hope that during this talk, I have highlighted the importance of the model-independent approaches, which allows us to detect and pinpoint what are the requirements by the cosmological models in order to reconcile all measurements. And as I was discussing with the first plot that I showed you, it's pretty clear or very unlikely that this tension right now is due to systematics, because those systematics will have to be appearing in many, many measurements for like many cosmological probes. So this is a very effective way, at least in my opinion, to see how we need to modify lambda cold dark matter in order to reconcile the measurements. Also, these tensions need to be confirmed as between the measurements depending on the early and the late universe, but in the same way, it can be framed as a mismatch between the two anchors of the distance ladder. But also, we can't think only on the summarization and radiation drag, because as I showed you, now we also need to care about the age of the universe and omega matter. There's no room right now for big changes at low redshift that may reconcile the Hubble constant. So this basically shows and demonstrates that pre-recombination changes, and most likely would be a boost on the expansion rate, are required, but are likely not enough, as I saw with the new measurements of the age of the universe, in order to reconcile all the measurements. So now we need to play this game both before and after recombination. And also, I haven't talked about this in this talk, but this model that will reconcile all measurement hopefully will not worsen other existing tensions as the one of the weak lensing. I didn't have time to talk about this, but line intensity mapping will grant us access to unprobed stages of the universe, and I hope that it will have a lot of relevance for the future of cosmology. And also, in the end, I just told you about the very relevant use that we can take of the new cosmic triangles. Thank you very much.
Okay, well, yeah, thanks very much for a very nice talk. Let me just stop the recording.